All
There we
right.
go.
Do you guys see the slides on the screen?
Yeah.
Yeah,
So I might
All right.
launch with an introduction of Marcus. Marcus is Brazilian, but then was a PhD student of mine in Australia at the JKMRC. Was really fun and interesting to work with and innovative.
Malcolm, I think you're muted.
All right. Thanks for the.
Malcolm?
How did I get muted? Did you mute me, Julia?
No.
I have to start again. So welcome to our March seminar. Thanks for Marcus for stepping in. We needed to move a day to accommodate him. But Marcus is from Brazil. I met him when he came to do a PhD at the JKMRC in multi-component modeling, and really inventive, innovative student, pushed the boundaries, doesn't know any conventional limits, and got into had the idea around that's become the GeoPura while there. And I really encouraged him on that journey. And he's taken some big career moves to get himself into a position where he can kind of follow his dream and his mission. Not easy, as he knows now, we all know, to go and follow your mission in life instead of taking the comfortable route. So got a lot of engineering experience, had practical experience before he came to Australia. Then I think it was 8 or so years with the Senko engineering design work. So a lot of practical background and understanding where technology might be really of value. And Marcus was also a fanatical long distance or ultra distance cyclist, which reflects in his life. So one of those people who lives what he believes in, shall we say. So really fun to work with Marcus, challenging, and I think he's going to throw a few challenges down for us today on what you can move to as an industry. So welcome, Marcus. It's all yours.
Thank you, Malcolm. Thanks for the introduction. So welcome everyone. Many familiar faces, and looking forward to meet you guys face to face for a toast in Cape Town next week. So I start by putting one slide where I kind of try to summarize a good panorama of breakage tests out there, which can be from large scale pilot tests all the way to geomet level tests, which is where GeoPura sits. But we can broadly classify these comminution tests into grinding tests, which can be done in batch, which can be done in locked cycle, such as the bone test. And in the SEG space, these grinding tests are represented by the SPI, SGI, and the StarKeys SEG design test. And in the single particle breakage test, which is where the famous JK drop weight test sits, and the SMC, which is a simplification of the drop weight test, we have also the rotary breakage test, which for a number of reasons didn't took off. And we have also the heat test, which is not even simplified, but a miniature version of the drop weight test, which Tony Kojovic introduced a few years ago. And let's say on the smart side of the single particle breakage test, before GeoPura, I think the only thing you had was the ultra fast load cell, which Professor Marcelo Tavares developed with Peter King in Utah. And then there are other tests that I'm not gonna cover here today, which are equipment specific. So you have those jar test mills for stirred grinding media, such as the ISAMill test, or other jar tests for Verdi mills, and also a HPGR pilot test to measure specific throughput to the HPGR and operating at different operating pressures and so on. But the bottom line is that characterization is a measurement of the ore property. So of course there is an interaction of the ore with this equipment, especially when you're talking about these equipment specific tests. But when we are talking about like a general way of like measuring the ore properties during breakage, that which I think the more purists like are the single particle breakage tests, which you are applying some energy and looking at the progeny of this the breakage event. Then you are really characterizing the ore properties. But in any way, like it has to be a quantitative measurement. It cannot be like some like a range or an estimate, like or so on. It needs to have a number which engineers can use like to size mills. And it normally like it's a prediction of energy consumption and resulting particle size distribution. So in the case of the bone test, I think is the oldest like of the breakage test like and still out there like as the one of the most used standard tests like in the planet. It relates like energy to fragmentation from a feed size to a product size. Energy in that case is represented by revolutions of a standard mill. So the bond mill is a standard mill, has a standard ball load in it, which even the size in the mass of the balls in each size like is very critical like to have a standard. Not sure if all the labs follows the right standard, and Alex Doe really like punches on that topic quite often. And then basically each revolution represents a certain amount of energy, which he ties in like in this equation, which like will give you his work index, which can be used like in comminution circuit modeling of industrial mills. In the case of like the drop weight is same thing, like you have an energy that's applied at different energy levels resulting in different fragmentation. The drop weight test uses the T10 as a marker, and then Narayan Whiten did a lot of work that like of the self similarity where we can go from T10 to all different T families, and then you can get the full particle size distribution starting from just one marker, which is the T10. But anyway, all these tests, like inevitably, they have like some limitations, and the main limitation is like the high cost to conduct them, which is mainly labor. So it requires a long time. I did a lot of bone tests and drop weight tests, like when I was a student at JK, as part-time job during the weekends, and takes a lot of time. The samples have to be large, and then so with those samples requirements, you don't have a representativity of the what you select. In the bone test, is less of a problem because you are crushing all the material to -335, and you will be rotary dividing the material, so you can assure that like even the refuse during the test, they are of the same quality of the initial feed and so on. However, when you talk about single particle breakage test, when you receive like a drum with like a 20, 30 kilos of rock, for you to select like in the case of the SMC 100 particles and expect those 100 particles to represent what was in that drum, it's a long shot. And that was to solve this problematic. That problem leads to an even bigger problem, which is the problem of not testing enough. Like we are doing like engineering and financial evaluations of mining projects with bugger all amount of comminution tests done. It's only done enough so that you can have an understanding of like the ore body or the ore hardness, so that you can size a mill, and that's done by using contingencies. So you put like the design criteria at the 8th percentile, or if you want to be even more conservative, at the 9th percentile. So if you measure 10 samples ranging like from 2 to 8, you design like for a work index of like 6. It's at that level of degree of conservatism, like in the design houses, like engineering companies where I used to work in a past life. However, when we come to predictions of like a throughput through the life of mine, like with a handful of samples, which is the reality, that's a long shot. That's impossible. So the entire financial of the project is based on like a nameplate throughput, which will not occur like whatsoever. Like it will vary up and down, and that will also happens to the revenue. So basically, when we looked at like feasibility studies and look what happened after, about like 40% of the projects, they are under nameplate throughput in the first 3 to 4 years, which is like a shame, like to for our industry and our category, like to see projects that do not perform according to the plan. And due to the huge connection that throughput has with financials, and that's very simple, like NPV is when you bring like cash flow like into the present value, and cash flow means like a money you make. It depends on how many tons you make. Like so, the tons of copper that you come out like in the concentrate is directly linked with the tons of ore that you're gonna feed through the mill, and that's related to the ore hardness. So that variation in throughput, because there is the aspect of like the time aspect on NPV, like it's all like a time discounted cash flow. So because throughput is tons per hour, tons per day, tons per year, it is very sensitive to throughput. So in sensitivity analysis, like in feasibility studies, the famous what ifs, if throughput like changes by 1%, the NPV can vary by 4%. So since you don't have that like really understanding of the throughput variability, your NPV can be all over the shop. Like so that's the reality, and that was the main motivation for me to come up with a test that would do the characterization of the ore properties in a fast, low-cost manner, using small samples, doing accurate measurements of the breakage properties and the breakage force, energy used like in the process of breaking those samples, creating that like the ideal test for geometallurgical applications, and so that we can do online data analytics and have like a large volumes of data. And that's like a picture of like the GeoPioro for those who have never seen one. It has two counter rotating wheels. It breaks one rock at a time, and then it weighs the particle, breaks the particle, measures the peak force for fracture. It measures like the energy absorbed by the particle during breakage, and that energy measurement is by laws of momentum of the wheels, that they rotate freely like when we are breaking the particle. And then so the difference in kinetic energy before and after, that's energy absorbed during breakage. And we are now like fully commercializing this technology by licensing it to laboratories and mining companies, and serving them with the data analytics that I will go more in the way I see the future. That's not only testing, but analyzing the data that comes out of the test. But people need these parameters from traditional tests. Like engineers need them. Like if you come up with something that like is very unique, and you don't have like models that people will use, like okay, I'm measuring like some specific energy and force fracture in the GeoPioro, but the engineers, they cannot do anything with those numbers. They need the bond work index, they need the A times P, they need the drop weight index. And that's what like we've been working like in the first years, and still now like developing ways to provide those parameters in the most accurate way as possible. And that's what I'm going to be presenting at like the Comminution conference next week. But you do one single test and you get parameters from a range of tests. So that's like a very good, because engineers that prefer using SPI rather than A times B, they can use the SPI. If they prefer to use the drop weight index, they use the drop weight index. If they only work with bond parameters, yes, we have the bond work index and the crush work index, which is not listed there, but we do. And we are catering also like for our colleagues, for the mine engineers that need like a UCS information, the mechanical strength information, both for a matter of safety, like in designing like the mine and the benches, the slopes of like an open pit mine, or like the galleries of an underground mine, and also for blast, during blast designing, like and optimizing that blast. So it's a jack of all trades, I would say. And in terms of sample requirements and going back to that topic of small samples, which is very critical, we decided to design the test so that we can use the very same samples that geologists use for assaying the ore. So we don't need separate samples. We can use assay samples, which usually are 1 meter sections of drill core, but not the entire core because they keep half like for in archive. Usually it's half core or quarter core, and we can use that like as much as a sample for our test. And we can do the test in preparation for the assay because the wheels, they don't accumulate material, like we don't have cross contamination, and we don't lose any material throughout the test. So we can do the test, put the material, the broken sample into a bag, and forward it back or send it back to the assay lab, and they can do the assay. We can work on a range of size fractions, even in between size fractions that the typical drop weight would not operate. And then we do a very quick sieving at the end. Like in terms of workflow, where is it? So we collect samples, like which can be like from drill core or pit. Like we crush those samples with a jaw crusher, very coarsely. We collect the samples and then we do a sieving to basically collect those size fractions. And then we get one size fraction above or below, like not to get our sample wet, to do an SCG measurement. And then we get the particles that are going to do the test, and we pass them through the GeoPiora device, which does the measurements of energy and force. We do a quick sieving, not a complete, like a full sieving, but just enough to capture like the percent passing in 150 and the T10. And then we upload the data into the Geodata software, which is our cloud-based like data analytics platform, and you get the results immediately. So the Geodata was a huge development that we did with the help of Thiago, which is sitting behind me here. And then we basically, it's a system that like our users can download templates, they can enter the data and get the results immediately, which it's a huge advance because when like a customer sends samples to do a bone test or a drop weight test, the laboratory does the test, and then like it goes like to some analyst to analyze the data, write the report, and send back to them. So the turnaround like it can get to be weeks or months, like depending on the amount of samples that are being processed. And with our test, you do the test today, in the next minute you get the results. Right. In terms of accuracy and precision, which was something that I was always interested in, and then comparative like to other tests, we are way more precise. Accuracy is a difficult thing to address, but I will get there, and I will mention a bit. Like that was actually the topic of my presentation at the Comminution conference in 2023. And then, but let's start like by explaining what we are measuring. So we are measuring the force for fracture and the energy for each individual particle within a sample. So in the end of a test work, we get a distribution of like energy measurements and force measurements per sample. That allows us to look at these distributions and see how much variability is within that sample. And also we can easily compare samples. Like we can do a t-test to compare two samples. We can do a ANOVA to compare a few samples, or use it like a variable analytics to cluster and separate them into groups when you have like hundreds or thousands of samples. But in a sense, like we are measuring force and energy. And then I wanted to evaluate like how precise is this force measurement? How precise is this energy measurement? And again, the concept of precision is reproducibility. So if I have measured energy and force for this sample, if I have a repeat on that sample, how close I am from repeat to repeat. And in terms of repeat, we did like the classical round robin. We did that like about like 2 years ago. We had like at the time 4 different devices and 6 ore types. We were a bit like a more thorough, like JK normally do round robin with a single ore type, They only use Mount Merrill basalt, but we had like in our hands like 6 different ore types, so our matrix got a little bit more complex, and we had like 4 devices, 4 laboratories in the play. And then the results coming out of this round robin were impressive. So basically, it like gave us like that there was no different significant difference across any of those labs when we did like a day nova. And then the it's not there on the slide, but it was in the order of like 5% difference across labs, like that, like the in the most different like lab one to the other. And then in terms of accuracy, like the experiment was a bit different, because accuracy like could be like I would need to know if the energy I'm measuring, because that's a completely different concept. Because most comminution tests out there, you provide a nominal amount of energy in the drop weight, like a mass falling from a certain height. In the bond mill, like is a charge, the charge of the mill delivering a certain amount of energy per each revolution. But in our case, we have some energy stored in the wheels in the form of, they are like flywheels with like they are heavy wheels, and they will have enough energy to crush the rock. But the amount of energy that will be absorbed will be different, like from sample to sample, even from particle to particle, as I had shown, like here within a sample, you get like different energy measurements for each particle. But we wanted to know, like, is this energy that I'm measuring really accurate? And then the only way to do that was in an indirect fashion. Like, so basically we had to assume that for the same energy, we were gonna get the same fragmentation, the same T10. So we separate some samples from 7 different ores, and we did the test like in a way that we did the geopiota first. We got the average energy for that sample, and then we adjust the drop weight tester to provide that same amount of energy as we have measured in the geopiota. And the result was that the T10s, they all matched, and that was a confirmation that our energy measurement is accurate. But as I said, this is an indirect way to do it. Like with the force, like it's more complicated to do. We are trying to look at it like now, like with Professor Marcelo, with like against the ultra fast load cell, which like has strain gauges to measure force. But like we test like the accuracy against like a known pressure gauge. So basically calibrate our load cells against known forces. So there is no reason why the force measurement not to be accurate once the load cells are calibrated. Yeah, so the average precision was 6.8% for specific energy and 6.3 for force measurements. And this is like a way better than the precision that you see when they do round robins of bone test and SMC test. Like the last works were presented by Tim Vizcarra were in the order of like 10 to 12%. I don't recall like exactly the numbers that he presented. And like what everybody keeps asking us to do and to see are the validation results. Validation in terms of like, do we provide equivalent results as the SMC and the bone test? And the answer is yes, absolutely. We are like, here is the figure of like the drop weight test. This is for our most recent work, like in terms of like a database. We are now with a database of comparative tests that they had like a SMC or drop weight done and bone test work done. And then we have like a relative error, like well, I wouldn't even call error, but a relative difference, because who is right and who is wrong here against the SMC measurements of like 11%, which is in the ballpark of the reproducibility of the drop weight test. And here is the A times B parameter from the JK drop weight test, and we are really close. As I said, like in the beginning, we were using standard fitting of A and B in the breakage equation. But since our database of comparative work increased a lot in the last couple of years, we implemented like a neural networks to capture everything that we measure in the GeoPiota, like the energy, the force, the fragmentation, the impulse, which is the integral of force over time. All these metrics that are measured by the GeoPiota, they serve as input to predict directly the drop weight index, and the quality became much better as if we were to fit A and B and go from A times B to the drop weight index. And same thing for the bond work index. In the beginning, when we didn't have much data, like we had a simple model, which started with 6 samples that I did at the University of Oulu 5 years ago, to correlate the size-specific energy on the closing sieve of the bond, typically 150 micron, to the bond work index. And so basically we were measuring the energy with the GeoPiota, we were sieving the material, we had the percent passing 150 micron, so we would calculate the size-specific energy, which is the parameter that like Grant and Malcolm introduced a decade ago maybe. And then we were correlating that size-specific energy with the bond work index. The correlation was okay, it was not bad, and was getting a little bit better as we increased the database from 6 to 25 to 80 to 200 samples. But now that we have like more than 800 samples, we can simply simulate that bond work index again from all these measurements that we do in the GeoPiota and go straight to the bond work index with a relative difference of 7%. And most of the samples like in the blue zone, which is 0 to 15% deviation, very few outliers. In terms of like case studies, we have.
Are we able to interrupt at all?
I don't know. You can.
I think it's better to wait to the end of the talk and then we can go for questions.
Okay, sounds good.
All right. Looking forward to hearing your question later, Grant. So in terms of case studies, we have like a few under our belt. Like there were a couple of feasibility studies that have been using GeoPiota test work data. Sakati was the most prominent one. Like it's one of like the deposits that was endorsed by EU, supporting the critical minerals. Like it's a polymetallic like deposit. And we already did like 300 samples for them. Actually, this has increased. We did actually now we are more than 400 samples tested, and we are correlating like creating geomet models with the mineralogy data that they've been doing, and they've done like thousands of mineralogical data on their deposit, and we have a very good AI model now which can predict like the comminution metrics from the mineralogy. Copperstone is in feasibility phase. Like they had done 120, but that number has also increased. They've done more test work like in our license lab in UK, and Freeport is doing like the feasibilities for those properties in Lone Star, and also did like more than 250 samples with us. We also did a couple of geomet projects with Agno Eagle. I presented some of that like at the SEC conference in 23. We are working on a follow-up paper because we use like classical ways of doing geomet, like with that Agno Eagle data, which was like simple regressions, and we use Kancha software. But now like we are revisiting the data and using the AI methodology that I developed with Thiago, and the results are getting way better in terms of predicting the comminution metrics from the geochemistry data. And then the Anglo-American, like they did like a lot of samples in Mohaloquena. We still haven't started doing like the geomet like work per se, rather than measuring like spatially distributed samples and have that as actionable data for them. But now we are starting to develop like these models to link geochemistry and comminution metrics. And in terms of mine-to-mill programs, we've been doing with First Quantum. We started in Panama, and then with the closure of the mine there, we shift to Sentinel. And they are already like in the excess of 5,000 samples, where they are taking chips of drill and blast chips, doing the test, getting data the same day, influencing the loading of those blast holes, and also tracking the data all the way to the mill feed so that you have actionable mill or hardness data, the mill feed. Another interesting piece of work that we did, like Thiago presented the IMPC last year. I will just show the highlights here, is the introduction of our own parameter, the GeoPura index, which is a number which links the specific energy that we measure with the SG and the T10. It has the same like units than the drop weight index, and that creates a tool for people to move away from using historical databases that they have with drop weight index and convert them into the GeoPura index, which is something that we are doing it ourselves as well, like with historical data of mill operating data, because now we are developing our own power models, like in terms of like a simple comminution model, power-based comminution models, like such as the Morel model or Osgrind model or the OMC consultants model, Derek Barrett model, simple models that like relates like the ore property, and in this case like the input will be the GeoPura index, and then you can calculate the SAG specific energy for different operating conditions, and also the entire circuit and the SAG, like mainly focusing on SAG and ball milling circuits to begin with, and we are in the process of developing these models that's in the cooks. And then well, like so here it's how the relationship, like this is another work that this is a work that like Leonardo has done for us to show the impact of like amount of sample numbers in the way to look at the throughput that you're simulating. So basically used Monte Carlo. We had this huge database that comes from the Skitila work that we had 900 samples tested. And then we were using random sampling to take like smaller data sets from this big data set, like so going half, 1/4, 1/8, 1/16, like of the entire data set, and look what happens to the variability of like a SEG simulation. And then you end up having like a huge like a variability on the throughput when you have low samples, like so depending on the on which samples you select for the test work, like your inputs can be different. And then when you increase the sample number, even if you have like across the different cases are like basically sampling from the full data set, like and then you have more consistency, because it doesn't matter like if I got like these 500 samples or if I got like a different set of 500 samples, my simulations would be very consistent. But like when we do with few samples, you can be biased like towards harder samples or towards softer samples just by the sampling that's being done like to do the test work itself. So another advantage of testing more. And then in terms of the value of like using this sort of methodology and doing more testing, like I would start like to talk about like a value for greenfield projects where people are doing assays. This is something that we work like very hard, like and it has to be with our philosophy of linking geochemistry to the measured like results of the GeoPura, so that we can scale it like the entire drilling database. So we are proposing to use like a 1 to 5%. And here is an example like for a case of like a 100,000 assays, which is typical in any feasibility study to have 100 kilometers of drilling. And then you take like a 1% to do GeoPura test, which would be about 1,000 samples, which is 2 orders of magnitude more than you see in feasibility studies. And then when that would allow us to a lot of confidence to develop like a good geomet models against the geochemistry. And then we would also be selling like the inferred data points. But in the end, like the customer would have invested like about like 600,000 to do the whole test work and develop like the AI model. And with that would come down like to a cost of 650 per meter to have full suite of comminution metrics and geomechanical metrics like on the entire drilling database. Like that's a game changer, and does not even compare with the cost of sample acquisition, like which is $400 to $800 per meter. And then when you add like the cost of assaying, which is around like at least 50 to 100 depending on how many elements you're measuring, that like comes down like a really low cost for the end user, and would allow a lot of value to be added in terms of like optimized like a resource definition, more strategic mine plan, and basically more accurate forecast of like throughput and revenues for the life of mine. So, and the geomet like side that I keep talking about, the correlation of the geochemistry to the comminution metrics, was presented like in the Minerals Engineering Journal, like was a work like that I work with Thiago, and we are exploring that more and more. Like now we're going to back like and reapply that in Kittilä. We are doing that in Freeport and with Anglo, and most cases like are really good results when we are using like either deep neural networks or PSO to, which is particle swarm optimization, to predict like comminution metrics from geochemistry. And in terms of to mill space, the whole philosophy like long time ago, but like you lack like a means to do tests, actionable tests in real time, near real time. And that's what the GeoPura allows you to do. Like that's what they are doing like in Sentinel as we speak. You can collect drill and blast chips, pass through the GeoPura. You can do the geochemistry or mineralogy to create like in parallel the geomet modeling too. But at the same time, as soon as you did the test, you have the information, you have the data to influence the drill and blast procedure so that you can fragment more the harder ore. And as everybody know, like when you decrease feed size in a SAG mill, like of harder ores, like you are increasing throughput, and then and you can track that information that you've measured like in situ, like for the rock, like on the bench, on production benches, through GPS systems, through the crushers, and into the stockpile. So that's the way we are doing mine to mill with the GeoPura. And what's next? Like that's the big question. Like so next, like I think most of you, like those that are closer to me, knows that this is like the holy grail that I've been working towards, which is the ability to use the GeoPura in a complete ore characterization done in real time. Since the most difficult part of this exercise is obtaining the sample from the belt, we will be adding a lot of value, like not only characterizing the ore breakage properties, but doing a full characterization, geometallurgical characterization of the ore, which would involve mineralogy, geochemistry, grain size, texture, and that we would be doing inside this portable laboratory that like we are calling like the GeoPura Rock, like the real-time ore characterization. And then we've been trying to raise funds for it, like through European Union. We got some, we managed to get increased TRL, but we still, it's work in progress. And yeah, so that's pretty much it. Like I'll finish like with a slide that shows our brilliant team, like that's working with us. We have like a good balance between technical and non-technical stuff. Excellent board, like which we have to thank a lot, like the works of like Rob Stephens and Rajiv. Like Rajiv was a former member of the company, but he left to continue working full time at Ozenko, but he's still member of the board. the advisory board, and the advice that we get from Rob Stephens and Rajiv are really, really valuable to help us shape the future of our characterization and pave the way to have this widespread in the industry.
Thank you, Marcus, for the very nice presentation. Yeah. So we have some questions here, and I think the first one can be Grant. So Grant, please, if you are there.
Thank you.
Yep.
Marcus, I just had a question for your earlier slides where you looked at the correlation between your drop weight index and the one measured. Yeah, that one. Can you just give some indication about how many? You said this was based on neural networks and kind of correlations there. How many parameters is required there, or are fitted to be able to get the GeoPura drop weight index? And how stable are those parameters? Like the results we get today, how different are they from the results that you would have gotten from that same test done a year ago?
Yeah, exactly. Yeah. So those parameters, there are two main ones, the force and the energy. They are the two main parameters. And as I showed here, the reproducibility of them is in the order of 6 to 7%. And these across like 4 different laboratories and 6 different samples, materials, like or types. And then these are the two main ones. In addition to the force and the energy, we are using fragmentation, which is T10 and percent passing 150 micron. So these are the parameters that we used as inputs to the neural networks, to train the neural networks to get to the drop weight index. So these samples, these 800 samples, they were samples that they have been through the GeoPura, they have been through the SMC. Some are leftovers, and those are, in most cases, the leftovers that we receive are the outliers. And I can talk a bit more about that, but focus on your question. So we have like measured the force, the energy, and the fragmentation for our samples, and then we know what the drop weight index should be. And then we train the network, the neural networks, and then we do we train it like with 80% of the samples, so like not with the whole 800. And then, which is classical in AI procedures in neural networks, and then we pick the other 20% that like we haven't seen that data in the training, and then we test the models, like, because we end up like with like 10 different neural networks, like and then we test like all of them against like that like a blind test data set, and then we pick the best model to use.
So maybe I didn't come across. So there's three parameters that are inputs to the model. Your force, your energy, and your T10. Oh, what's happening? Why do I have balloons?
Because you're going too long. I don't
know. Sorry, that distracted me. But how many fitting parameters are? Because obviously you can do like force, a times force, or a force squared, or square root of force.
No, this is not regression. This is not regression. No, it's different. Like you need to understand what neural network is. Each variable is a dimension. So it's a multivariate, like a data analytics technique, that he looks at relationships between all the different variables, which means dimensions in the space. Like, so he's looking at and creating these connections between all these different parameters. It's not like an equation that like has this, that parameter, and you can have to the power of A multiplied by B, and you have like a many fitting parameters. Like it's not regression. It's not classical regression. the neural networks works in a way that it is training the network to find the weights and the relations between all the variables that we are considering. And the variables that we are considering is the energy force, two markers for fragmentation, which is the T10 and the percent passing 150. And then we are additional to that, we have a variable that doesn't change much, which is the particle size. So we want to tell them also, because then we can embed particle size effect. If the test was done on the 22.4 by 19, the particle size would be the geo mean of that, 20 mils. And so on and so forth. So basically it's creating these connections that interpreting those connections. There is not an equation with a number of parameters to be fed.
Okay. The second part of the question, sorry, I'm taking a bit of time, but was how stable is that with time? Are you expecting that to change much? Has it changed much in the past? And how can we have confidence that the results we get now are going to be the same results we get with a future neural network?
Yeah, it is not changing substantially. It has some leap of improvements from the first or the second version. But as the database grows, it won't change significantly, because unless there is something completely different coming into the database. But it is what it is. We already have ORs that goes from drop weight index 2 to 14. So basically it is pretty stable now, the neural networks. If there is incremental improvements and refining the model, we haven't seen much of a difference. Even because now we did the update with 800. The last time we had feed the neural networks, we had in the database around 500 to 600, and then when we recalibrate the neural networks, we recalculate historical numbers that we had, and the results are not substantially different. It was very close to one another. And we do these checks, we do these checks of before and after. Every time we calibrate a new neural network, we have the entire database. We do these calibrations of checking before and after to see if there is a substantial shift, in the database as a whole.
All right. We have two more questions here. The first one is Simon, Misha Simon, I think. I'm not sure about.
Yeah. Hi guys. Hi guys. Hi. So back in the day, can you hear me okay? Is all good?
Yeah.
Yeah. Okay. Hello, Marcos. Very nice presentation. Back in the day, I was a technician at the JKMRC, and I've done a couple of 100 drop tests. When I was doing a bit of research too, we were trying to sort of work out small-scale tests. What we found was the inherent variability of both the drop test and the bond test was internal. Right, and the problem was when you actually get a sample for a drop test, you get like a 44-gallon drum, and some of the particles are as large, 53 to 63 millimeters. You're handling the rocks and you're putting them through, and you can see their different mineralogy, and you don't have very tight controls about where that mineralogy is coming from. Then you've got the problem of what the drop test actually does and how it actually breaks the rock. There's variability within that test itself. So what it is, you've got a shotgun blast of a very young Steve Morrell there. Look at that, gosh. You've got this variability that you're trying to actually sort of tighten up on, but the variability may well be inherent to the drop test itself. The same thing was in the bond test. We went round and round and round in circles until we did an internal assessment of what a drop test actually was. There was a problem. So I'm also saying is you might be flogging yourself over something that actually can't be solved. Now, when we were doing geomet analysis, the most successful results happened when we took something like an SMC test, and you took the parameters from that and you combined it with some sort of assay information or a ratio of assay information, and put those two together to predict the mill outcome, and that relationship tightens up beautifully. So what I'm saying is you're doing well, and you might be as far as you can get. But the next step would be adding some sort of routine rock information that describes the mineralogy. Routine, like assay.
Yeah, we are doing it. That's the whole idea of like this procedure of using small samples is to tackle these two issues that you just raised. So when you use small samples, like and I pick like 30 particles from that 1 meter core, that represents in mass 30% of the 1 meter core. These 30 particles. But when I take like 100 particles to do an SMC and the mother sample is 15 meters of core, I'm talking about like 2 kilos, which is the total mass of like an SMC test, like 2 to 3 kilos out of like a 60. So we're talking about like 1 to 2% like of the mother sample was in fact tested. And then the other thing that I was trying to touch, and I left aside, but now is the right time to say, there is a procedure in the SMC that very few people know about. And then I'm just thinking like how I will like put that like in a polite way. He doesn't publish it in anywhere. Like only people who do SMC in the laboratory, like those that actually got dirty in the lab, like doing SMCs, know about this procedure, which is the particles that he selects for the test, they have to be within plus or minus 30% of the average particle mass. The average particle mass is determined with an initial random picking of 30 particles. And Tina Peman already showed that, like, if I pick 30 particles, you pick 30 particles, and he picks 30 particles, each and every one of us will have a different average particle mass. And then, but anyway, let's establish that average particle mass. And then he goes back to that drum, like that sheet drum that you've mentioned. And then he goes picking 100 particles within that size fraction. Let's say that the average particle mass established was 20 grams. The operator has to weigh each particle that he wants to go to the test and check if it's within plus or minus 30%, meaning between like 14 and 26 grams. If it's above 26 grams, below 14 grams, it's not selected for the test. And then you only do the test on those particles. What that means. So he tried to do that to make like sure that like the sample was consistent in shape, because shape changes the particle mass quite significantly, even for homogeneous specific gravity. But if you have but because of the nature of like starting from a large sample, you end up biasing the SG mineralogy selection. So basically, if you had particles that had like a magnetite intrusion or was a massive sulfide, high SG, they will not be selected. Or if you had like particles that had like, I don't know, graphite in it, like or had like oxidized like or some micas that like were low SG, would not be selected for the test. So you're inducing a bias without telling those who use the test that you are doing it, because nobody knows about it. Like I could do a survey here, like of everyone in this room, like who knew about it. Like nobody knows about this procedure. And then when we get leftovers from the SMC, quite often we get like outliers, which you see there's some outliers like in our prediction of drop weight index. And in those cases, I would challenge like the person to go back to the sample and do a repeat on the SMC and make sure that they get the same result. They will not. Because like when you get the leftovers, you don't have that like a sweet spot between plus or minus 30%. The particles will be heavier, lighter, but will not be of that same quality. You are testing, in fact, a different material. And very few people understand that issue. And then, and that's why we want to keep our samples small to begin with, so that when we pick our particles, we are representing what is there. And yeah, so that's the main issue, like when we're talking about SMC test and this particle selection thing.
Yeah, so I would much rather have an SMC test from a precisely known, geometrically known sample, like a piece of drill core, right, where we can place it in the deposit and it's got some mineralogical context information. I would much rather have that information many times rather than a vague sample that's been sort of taken, like, you know, where we can't pin it as directly as that. It's much more useful. What I'm saying is the SMC test is actually more useful to me as an analyst than the drop weight test.
Oh, for sure. But
Yeah,
even the SMC, Simon, the SMC, it requires a large composite. Like you say, it's not pinpointed.
Agreed.
Like
Agreed.
You cannot do an SMC on 1 meter of core. You're gonna need like a 15 meters of core. I had that issue that like using iogas and trying to correlate like the geochemistry or the mineralogy, I would have that information on a meter by meter basis, and then I would come like with my SMC data, and that represents 15 meters of that core. And then like what do? You repeat that SMC number 15 times, or you average assays, which like either or like it's not ideal. Like so that's why like if you do like your comminution test on 1 meter samples, you're gonna have the geochemistry mineralogy for that very same sample.
Yeah, agreed. And so what you do, you're chasing something here that's very difficult to nail statistically. Anyway, great presentation.
All right, thank you. So 2 more short questions here from Wesley and Christopher. So please, Wesley.
Hey, thank you for sharing your presentation with us, Marcos. Congratulations. So regarding about the geometallurgical models, my question is, for the hard ores, and when you have, for example, 3 or 4 the main domains in the deposit, it's very difficult to obtain only one models for both domains. This is my experience with in some copper deposits. And how about your experience? It's necessary to have 4 models, each models for each domains, or you always have only a model to represent both domains?
It goes on a case by case, Wesley. Like we had both experiences. We had the one work like which was the Kitila, which we had like to have 2 domains, which was one for the mineralized zones and one for the non-mineralized. And then we had to just 2 models. But like depending when we have like a huge volume of data, the neural network itself will understand those relations. So basically, it will understand like there will be this domaining. But if necessary, what we do to domain like is that like we use like K clustering, and then we can create these clusters, which is the definitions of boundaries in domains. That like we can classify them. Like we did like this work also for Anglo American, like where we could use the data, the particle data, because like they had done 300 samples, but at the particle level we had tested like more than 8,000 particles, and then we could cluster the particle data in clusters, and they held into space, and they held like we are checking in the XYZ, like in the space of the mine, in the deposit, they were holding together. And then once we classify these domains, like we could see that they each of them, like these classes according to hardness, they had like different signatures in terms of mineralogy. And then you can even see like these 5 classes there, like in terms of like images as well, like some examples there. Like it was really interesting work we did with Anglo in this polymetallic work.
So because sometimes we try to obtain models, and we are usually to take some characterization of the rock textures, and we have very different rock textures for the same minerals. For example, for the same rock, the minerals composition in the rocks, different littles, and we have totally different models in this case. And we check
that's interesting. Yeah, texture is definitely a thing. I think Simon spoke here before. They looked a lot into it. Like it's not only the mineralogy and the composition that like drives comminution, but the texture. So that's also like I didn't put here in the seminar, otherwise it's become too long. why we see a lot of synergies in between what we are doing and drill core scanning technologies. We are creating like a lot of like MOUs with with the two that we are working more closely are Veracio and also like the people from Finnish one called Lumo Analytics. And then when we have that information is another layer of information that's really useful like to creating like these geomet models.
Okay, thank you.
Thank you, Wesley and Marcos. So Christopher, please.
Yeah.
Yes, thank you for the presentation, Marcus. I have a mechanical question on the energy measurement of the rig. I was wondering if, I mean, you had quite high forces coming from the crushing of the particles. I was wondering if, do you do any compensation for the load dependency in the bearings, for example, when looking at the reduction of the speed, rotational speed?
Yeah. Good question. So basically, we do a friction compensation. So we calibrate that friction compensation at different ranges of speeds. Like so, we do that calibration, and we know like how much friction we would lose, and then we discount that like when we are establishing the net energy, which was the energy that like actually was used in breakage.
Yes. Have you also done that with different loadings on it, like with the normal force from the crushing?
Not really, because like yes, there is a very high force, but it's super fast. The time that it takes from pinching the particle and reaching the peak force for fracture is microseconds.
Fair. All right, thank you.
So the loading is very it's minimum, like that low.
Tiny. But yeah. I was just curious how big it could be. That's why. Yeah. But I guess it's hard to test as well, because you would need to continuously. You would want to measure the friction in it when you load with the same sort of force, which is hard to do.
It would be very hard. Yeah. Indeed. Yes.
All right. Thank you very much.
All right. So thank you, Marcos, for the very interesting presentation. A lot of good discussions. Malcolm, are you there? Would you like to close the session?
Yes, thank you. Thanks, Marcus, for stepping in. I forgot in the intro to say that Marcus this is his seminar is becoming a new full member of the GCC. So he's a new full member. Giapiora has been a member for about a year now. Marcus is a full member. So welcome him on board. Some nice new technology to tickle our fancy and think about the really useful stuff we can do with it, and good to see people really pushing the boundaries of how we think. Thanks, Marcus, and thanks for everyone to coming a day early to accommodate us all dashing off to the Comminution conference. So much appreciated. And thank you, everyone. Cheers.
All right. See you guys in South Africa. Bye-bye.
Yeah. See you. Thank you.
Bye.
Thank you. Bye-bye.
Bye, friends.